Have you ever stared at time series data that just refuses to behave? Maybe it trends up, then down, or it has these predictable spikes every year. That's non-stationarity, and it can feel like chaos. Today, we're digging into the framework built to tame that chaos. Autoregressive, integrated moving average models, ARIMA, and its more complex relative, SARIMA. Our mission here is to really lay out the theory, the concepts, and the step-by-step method you need to handle this kind of tricky, non-stationary data.
That systematic method is crucial. We've talked about ARIMA models before, and they demand stationary data where the basic statistical properties like the mean and variance stay consistent over time. ARIMA lets us move beyond that limitation. It helps us tackle data that isn't stable, and the real workhorse doing that is the I in the middle, the integration part.
Okay, let's focus on that I. What that's telling us is that our original messy time series, let's call it XT, it only becomes a well-behaved stationary ARIMA Q process after we've differenced it.
Exactly. Those three parameters, P, D, and Q, are like instructions. P is the order of the autoregressive part, how much the current value depends on previous values. Q is the moving average order, how much the current value depends on previous random errors or shocks. And D, the integration order, tells us how many times we need to difference the data to get rid of that non-stationarity, essentially to undo the accumulation that caused it. If D is 0, well, then we just have a standard stationary ARMA model.
Right. Now, that term integration, it sounds a bit like calculus, but in time series, it means something simpler, doesn't it?
It does. In this discrete time series world, integration really just means summation. Think of an integrated series as one that's been built up by adding things together over time, step-by-step accumulation. This accumulation often creates trends or makes the variance unstable. So differencing is our way to reverse that. We calculate the change from one period to the next to strip away that summed-up effect and hopefully reveal a stationary core.
So we're literally calculating differences to undo the summing.
Precisely. A process where you need differencing, where D is 1 or more, is called difference stationary. It might have what we call a stochastic trend, a trend that wanders randomly. The classic textbook example is a random walk. Imagine just adding up random noise period after period. It goes up, it goes down, but it never really settles around a fixed average. It accumulates.
Just keeps wandering off.
That's it. And a random walk is integrated of order 1, meaning D1. If you take that random walk series, XT, and just calculate the difference between consecutive points XT minus XT1, what are you left with?
The original random noise you started with.
Exactly. You got a stationary white noise series. That single act of differencing tames the random walk. That's the power of the I in ARIMA.
Okay, so conceptually, the full ARIMA equation pulls all this together. It uses differencing first to stabilize the series, and then applies the AR and MA parts to model whatever short-term dependencies are left in that now stationary series. It combines past values and past errors after accounting for the trend.
It's a really elegant structure. You handle the non-stationarity, then you model the stationary remainder.
Right, that lays out the theory nicely. But knowing the letters P, D, and Q isn't the same as finding the right numbers for them with real data. You can't just guess.
Absolutely not. And that's precisely why the Box-Jenkins methodology was developed back in the 70s. It's a systematic, step-by-step, iterative process for building these models correctly.
Iterative being the key word.
It's not always a straight path. The whole thing starts with one fundamental rule: achieve stationarity first. So step 1 is all about finding the right order of differencing, finding D.
Now, we have software that can suggest model orders. Is it still critical to actually look at the plots like Box and Jenkins insisted?
Oh, absolutely critical. Non-negotiable, I'd say. Automation can help, but your eyes are the best judge of stationarity. You start assuming D0, no differencing needed. Then you plot the raw data. Does it have an obvious trend? Does its autocorrelation function, the ACF, just decay really slowly? Like the correlation stays high for many, many lags.
Yeah, that slow decay is a classic sign, isn't it?
It's a dead giveaway for non-stationarity. If you see that, you need to difference. You try D1, calculate the first differences, and plot the results again, the difference series and its ACF.
And you keep doing this.
You repeat until the plots look stationary. The difference series should look like it's hovering around a constant mean, and crucially, its ACF should drop to near 0 relatively quickly, usually after just a few lags. That sharp cutoff tells you you've likely achieved stationarity and found your D.
Okay, stationarity achieved. We have our D. What's step 2?
Step 2 is identifying the orders for the ARMA part that models the remaining structure in our now stationary difference series. We need to find P and Q.
And this is where the ACF and PACF plots really come into play for the different series.
Exactly. The autocorrelation function, ACF, and the partial autocorrelation function, PACF, of the different series become your main tools. They have characteristic patterns. If the ACF cuts off sharply after Q lags, while the PACF tails off, that suggests a moving average process of order Q, so MAQ. Conversely, if the PACF cuts off sharply after P lags while the ACF tails off, that points towards an autoregressive process of order, P. Sometimes you see patterns that suggest a mix, an ARM, AOP.
It's like decoding signals from the data.
It really is. And this systematic approach can lead to some interesting connections. Remember we talked about simpler forecasting methods?
Yeah.
Well, if your Box-Jenkins analysis points you to an ARION 111 model, there's one difference, no AR terms, one MA term. The forecasts you get from that model are actually mathematically equivalent to simple exponential smoothing.
Wow, really? So it provides a more formal justification for that method.
Precisely. And if you find you need two differences, two MA terms, that's equivalent to Holt's linear trend method.
Oh.
So this sophisticated framework often connects back to and validates these well-known forecasting techniques.
That's fascinating. Okay, so after identifying PD and Q, we fit the model. That brings us to steps 3 and 4, estimation and diagnostics.
Right. Step 3 is parameter estimation. The software calculates the best coefficients for the AR and MA terms you identified. But step 4, diagnostics, is arguably the most important check.
Checking the leftovers, the residuals.
Exactly. The residuals are the errors the model couldn't predict. If your model is good, if it has captured the real structure of the data, those residuals should just be random noise, white noise. That means they should be uncorrelated with each other, have a constant variance, and ideally be normally distributed. You plot the residuals, look at their ACF. If you see any pattern left, any significant autocorrelation, your model is missing something.
Mean you have to go back.
You have to go back, revisit the differencing, re-examine the ACF, PACF, maybe try slightly different P or Q. It's iterative. You refine until the residuals look like pure, unpredictable noise. That's the sign of a good fit.
And once the residuals pass muster, we finally get to step 5, forecasting.
The payoff. Because we've built this model carefully and checked that it fits well, we can use it to predict future values. And because the model structure usually leads to forecasts that are approximately normally distributed, we can also generate prediction intervals.
Which gives you a sense of the uncertainty around the forecast.
Correct. You get the point forecast plus a range, a confidence band based on the estimated variance from the model. Very useful.
Okay, ARIMA handles trends, those stochastic wanderings. But what about data with really strong predictable cycles? Like retail sales spiking every December, or energy usage peaking in summer and winter. That regular rhythm.
Ah, yes, seasonality. For that, we need to extend the ARIMA framework further to seasonal ARIMA or SARIMA. It adds another layer to handle that periodic behavior. The notation expands. We write it as SARIMA, then the non-seasonal orders, PDQ, followed by the seasonal orders, PDQ, and finally a subscript ES indicating the seasonal period.
So SARIMA, PDQ, PDQ. If it's monthly data with an annual cycle, ES would be 12.
Correct. S is the length of the cycle. 12 for monthly, 4 for quarterly, 7 for daily data with a weekly pattern, and so on.
And we have new parameters, P, D, and Q for the seasonal part, alongside our familiar PD and Q.
Yeah.
How does the seasonal differencing D work? Is it like the regular differencing D?
It's similar in concept, but targets the seasonal cycle. Regular differencing D looks at the change from one period to the immediately preceding period, XT1. Seasonal differencing D looks at the change from one period to the same period in the previous cycle, XTXES.
So for monthly data, ST12, it's comparing this month to the same month last year.
Exactly. You calculate XT minus XT12. The goal isn't just to remove the correlation at lag 12, 24, 36, etc., but to make sure the ACF at those seasonal lags decays quickly, just like we needed for regular stationarity. It stabilizes the seasonal component. And a practical tip. Usually you don't need much seasonal differencing. Often D1 is enough. Sometimes D0 if the non-seasonal differencing also handled the seasonality. Over-differencing, especially seasonal, can actually create problems adding artificial patterns.
Okay, so be cautious with D. Let's say we've applied our non-seasonal D differences and our seasonal D differences. We should have a stationary series now, accounting for both trend and seasonality. How do we find the seasonal AR and MA orders, P and Q?
We go back to our trusty ACF and PCF plots, but now we look at the ACF-PACF of the fully different series after both D and D differences. And here's the trick. You need to focus your attention only on the seasonal lags.
So ignore lags 1, 2, 3, and look specifically at lags S2s 3.
Precisely. Look at lag 12, 24, 36 for monthly data. The non-seasonal P and Q should have handled the short-term correlations. Now you're looking for spikes only at those seasonal multiples. If the ACF has a significant spike at lags and then cuts off at lags 2s, 3s, that suggests a seasonal MA process of order Q1, so A0D1 seasonal part. If the PACF has a significant spike at lags and cuts off, that suggests a seasonal AR process of order P1, A1D00 part. You applied the same logic as finding P and Q, but restricted just to those seasonal lags. Often P and Q are small, maybe 0, 1, or 2.
So the full SARIMA model is really like two multiplicative structures working together, one for the short term, PDQ, and one for the season, PDQ.
It's a great way to think about it. Conceptually, the model equation involves the non-seasonal ARMA and differencing operators, multiplied by the seasonal ARMA and differencing operators, all working on the time series XT to explain it using white noise Z. It elegantly combines both structures. So wrapping up, ARMA and SARIMA models give us this incredibly powerful and flexible toolkit. They allow us to systematically break down complex time series, handling trends, handling seasonality through differencing, and then modeling the remaining stationary part with ARMA components. It's a process that really demands careful thought and checking, especially with the plots, but the reward is often a very accurate and interpretable forecasting model.
Right, and that ability to synthesize all these complex dependencies, trend, seasonality, short-term autocorrelation into one, often quite parsimonious model structure is really the strength here. We saw those neat equivalencies like ARIMA 0, 1 week 1, and exponential smoothing. It shows the rigor behind the method. Often these models outperform simple regression approaches on time series data precisely because they force you to explicitly deal with that correlated error structure that regression ignores.
Dealing with the autocorrelation is key.
So you've gone through the rigorous Box-Jenkins steps, you've carefully examined your plots, you've checked your residuals. Maybe you find yourself with a couple of good candidate models. Perhaps a SARIMA, Liveral 101 looks just as good on paper as a SARIMA Liver 101 based on the diagnostics. We'll leave you with this final thought to consider. When faced with multiple statistically adequate models, what criteria beyond just the diagnostics will you use to choose the single best one? How will you justify that final model as the most representative, the most useful for your specific forecasting needs? Making that final choice is the last step in bringing order to that initial chaos.